Hi everyone, welcome back to the second programming training session for the starter bot, the FTC starter bot for the Gobilda one. We were going to do the session live, but there wasn't enough people joining, so I decided to just record it rather. That made it more sense. So in this second session, we're going to finish off the teleop control, which is controlling the gripper and the pivot on the gripper. And then we will move on to autonomous and starting to program autonomous as well. So let's hop right into it then. So if we go over here first and we come down just to see the hardware like we did last session, what hardware are we controlling and what we actually need to do to control that hardware. If we scroll down till we find the gripper, you can see the arm, we've got the gripper here, right? We've got a servo, and this is the gripper assembly right here. So the sample will get rolled in by, you can see we've got a servo here that is rolling the sample in. It's the intake, and then we've got another servo right here that is controlling the tilts of the intake or grip or whatever you want to call it. So basically what we want to start with is, you can see here, here's the actual a better view of this servo. So the servo mounts onto here, and then when the servo spins this whole assembly right here, it will turn out the way. And the reason for this is that it needs to turn out the way to fit in the full size limit when the arm's folded up, and also needed for when you want to place specimens on the high chamber. So then, if we jump into the code over here, we've got our code from last week. Let's go here, the starter bot, the Gobilda starter bot. We have the drive motors, we have the arm motor, and we have the directions of the motors. Then we also store the positions for the arms using this arms ticks per degree thing that we got from the Gobilda sample code, which is great. And then we can set the target of the arm based on a driver input. So now what we want to do, like I said, we're controlling the servo, the intake servo. So we can create both servos, since there is two, right? One for the gripper and one for the intake, and one to rotate the whole assembly. So we say servo, and we'll say gripper rotate. Okay, and then we say continuous rotation servo, because for the intake, right, you want the servo to spin, not to set to a position. So that means, continuous rotation means it's continuously rotates, not set to position, like you would have a normal servo. So then we say intake. And then down here, we want to do the same thing with our configuration, right? We want to say ripper rotates equals hardware map get servo. And then we want to call this whatever we would call it in our config, which is what how the program knows what port to communicate with. So this would be, oh wait, this is ripper rotate, yeah. We'll just call it the same thing. And then we'd say here we've got intake, and this would be intake as well. And you change this to continuous rotation servo because it's a continuous rotation servo. Okay, so that's all the initializing you need to do for the servos. The ranges will be pre-programmed using the Gobilda servo programmer. I don't know if they have a picture of it here. I don't think so. You can see here's another picture of the assembly. This is the servo that rotates it, and then this is the intake right here. I don't have a picture of the servo programmer. Let's just open this up quick. Oh man, let's see. Okay, as you can see here, I'm pretty sure this comes in the kit, the Gobilda kit. So you plug it into with these batteries. You plug the servo into this right over here, and you can program the ranges using this thing. There's some videos online on how exactly you would do that, but you can program the range of the servo, which allows it to be a lot easier to control it in the actual software. Okay, So if we go back in here, then what we want to do is the controls we want for the intake, right, is we want, well, the most intuitive and what I would suggest doing is you say if gamepad1 dot left, what is it called again? It's called d-pad left. D-pad left is pressed, then do something, and you want an else if gamepad1 dot d-pad right is pressed, and then you want an else as well. So in the left one, you want the servo to spin in, right? This is the intaking servo. So we'd say intake dot set power So because it's a continuous rotation servo, you can actually set it to the a power like you would a motor. So in this case, you would set it to 1 basically, because you want it to go forward, you want it to intake right. And for this one, you'd want to set -1. So this will spit it out. And then if you're not holding a button, then you want to set it to 0. So this allows the driver to hold D-pad left and it will spin in, and then you can get to the right place and it will pull the sample into the intake. Then when you let go, it'll just stop. And then when you hold D-pad right, it will spit it out again to actually deposit the sample in the basket. Right. So that's actually all the controls you need for the intake servo. Now we're on this servo, which basically has to rotate 90 degrees. This servo normally has about 270 degrees of range. So what we would want to say is we can actually store them. You see how we've got the int position for the arms. We can do the same thing for a servo, except we need a double because we need to store a decimal point. So we say double collect position. Collect. We'll just say collect rotate, because we're already using collect position for the slides, for the arm. We say equals, and now this collect rotate, we can just assume, let's just assume it's 0, right? And collect rotate would be when it's like this, right? When it's pointing outwards. This is for collecting. So collect rotate, we can say is 0, and then we want another one for the deposit specimen or collapsed in, right? Stored in. So we'll just say deposit, because it's the easiest way to call it, and you want this to rotate 90 degrees, except it's not going to be 90 because servo is taking a position from 0 to 1. So because it's a 270 degree range servo, we basically, that's 90 degrees is about a third of its range. So we'd say 0. Sorry, move that 0.33, and that'll move at 90 degrees of its range. So now we've got the positions right for each of our things. We want to take our servo. We're going to say if gamepad1 pad1, sorry, dot we can say left bumper. So we can use the bumpers to control the tilt, right? We can say else if gamepad1 dot right bumper. So if it's left bumper, then we can say gripper rotate dot set position to, let's say, collect, right? And then if the driver presses right bumper, then set the position to deposit. So that way they can toggle by using the bumpers on the top of the controller where the gripper rotates positions, whether it's collect or it's in the deposit position for specimens like this. And the deposit position will also be used to deploy, not deploy the robot, to hold the robot within size limit when the game starts. So that about covers all the controls you need for that. It's quite straightforward, quite simple. The only other controls you might want for this IntelliOp is your hang control, right? The hang is interesting because it flips over backwards and it goes over the bar. Yeah, I don't think there's an example of it here. I don't know where it is, but it allows you to, you can see when it's like this in this position, it'll go over the bar and then you'll just pull this arm down. So you might want a slightly separate position. You can see up here we have a start position, a collect position, which is all the way over, and then a delivery basket and a collect chamber. Now, you could actually use those positions for the hang, since you want a position that will allow your arm to go over this bar, right? Which is about this delivery position, maybe a bit higher. And then you can use the collect position to pull your robot off the ground. So maybe let's just create one more position that's slightly higher than these deposits. And we'll say hang position. And we want this to be higher, right? Because you can see this angle here, the claws down here to go into the bar, but we need to get it to up there. So we'll change this to like, reduce it to about 140. So it's like flat, and you drive against the wall, and then you set it to collect position. And again, the way you would use this over here is you could just copy this, and you could say, okay, no, now for gamepad B, I wanted to set it to that hang position. And then when the driver presses B, the motor is going to go to the hang position. And then they can use the collect position to pull themselves up. So they press B, they drive to the hang, they then press A, and then it pulls down on the bar and lifts the robot off the ground. So that is actually everything we need to cover, or everything you need to do to actually program this robot's teleop. So I think for this session, I've still got some time on the recording. So what I'm going to do is just talk through some of what you would need to do then after that to do an autonomous. So the only thing that would be different for an autonomous is that you actually need to be able to navigate to a certain position on the field using your drive face, right? The rest of your controls are all pretty much the same, which means you can just use the same code. Just instead of triggering commands of driver input, you have to do them in a linear fashion, one after another. So let's do an example autonomous for the starter bot. Let me just pull up into the deep FTC field images. There we go. So let's open this up. Oh, yeah, okay, we'll just use this image. So we can say, right, the robots can start anywhere along this wall or along this wall, depending on which color you're on, right? So if you're on the blue side, you start touching this wall here. You just can't be in these end zones. And red is the same. You just can't be in the zones. You can't be in the observation zone or the net zone. So let's say, for instance, you preload your robot with a yellow sample. So basically how the preloads work is you can have your alliance, your team of robots, right? The two robots you and your partner. You start with 2 colored samples or alliance specific samples. So if you're on the blue side, you'll get 2 blue samples, 2 clips, and then 2 yellow or alliance neutral samples. So you can either choose to preload your robot with a sample without the clip, right? So it's just a sample, either yellow or your alliance color. Or you can preload a specimen, a sample with a clip on your robot if you want to as well. So why you would do this is you could either start against this wall, right, and drive here and drop a specimen or the preloaded specimen of your robot onto this onto the chamber, right? Or you could start here with a sample, a yellow sample. You could do it with a blue sample, but it is not as effective strategy-wise. So you want to start with the yellow sample, and you can take the yellow sample and place it in this high basket over here. And now the interesting thing is that the chamber or with the specimen is slightly more difficult because it's got to be more precise. But you do get 4 more points for it overall. So for this, for the high basket, you get 8 points for placing it in, but it gets recounted in teleop, which means you get 16 points per one you place in the high basket in autonomous. And if you do a clip on the chamber, you get 10 points for clipping a specimen, but it also gets recounted in teleop, which means you get 20 points for every specimen you place in autonomous. So it's a bit of a trade-off there with how difficult it is versus how many points you get. For the most part, you just start with the samples into the top basket, I think. So maybe that's something we can focus on now. So if we assume, right, with this robot, you have 2 wheels, these 4 wheels you're controlling, but it's just with 2 motors. So you need to use the encoders in the motor to figure out the distance you need to drive. So we can assume that this is the back of the robot right here, right? And if we start the robot right here on here next to the high basket with the back facing to the right, it's the easiest because we can just flip the arm over, which already has a sample in it, and then just deposit in the high basket. So then what exactly is the code that's needed for that? And let's start with just creating the basic structure, and then I can talk a bit about the navigation. And then I think I'll end there today, and we can after that, and we can spend more time next week, probably the last session, just finishing off the auto with all the ARM controls and stuff. So let's start here. We say new Java class. We say starter bot auto, and this is the Gobilda. Okay. We say extends. This time we say linear op mode. So before you see we have over here, we have op mode. We're extending op mode. In auto, we're going to extend linear op mode because we don't want it to repeat looking for driver input. We just want it to run through once. We can say implement methods, say okay. That's going to implement methods called run op mode. And this basically, instead of in the telly up here, we have an init place, right? Where the code gets initialized and it tells the code what ports it's communicating with. And then a loop period which just runs in the loop until the driver stops the program. In linear op mode, you just have one that runs through once. So the first thing we want to add is we can just come into our telly up right here, go up to the top, and grab our drive motors, right? We can put our drive motors at the top, same thing. Then we're going to take our drive motors over here, grab them, put them at the top of this run op mode method. Then we want to take our drive base, the rest of our drive base initializing code, put it underneath here. Let's do a letter. There we go. Great. So now the other thing we need to add, right, is because in a program when you start it, you have the initialize period and the loop period. If you don't add something called a wait for start right here, then it will just run all of this in init and then just crash the program because it didn't have a loop period or an init period. It just had the init and it crashed. And then it crashes and says, did you put a wait for start in your program? So you need to put a wait for start, and then everything above the wait for start happens when you start the program once on your driver station. And when you press the button again, then it will run everything after the wait for start. That's basically the basic setup. You're going to create your motors or your hardware up here, and then you're going to initialize it above the wait for start. And then your actual auto code that runs linearly, right, will happen down here afterwards. So now, just to quickly discuss how exactly, I mean, with this movement, right, we're only going to have to move like 10 centimeters. But we still need to figure out how we can actually get the robot to move 10 centimeters because it can only understand ticks, right? So that's where we'll start here. We'll say, okay, we have these two motors, right? And they have these things called encoders on the back. I talked about them in the last session, but we didn't actually use them because it's doing driving from driver input. It doesn't need to know exactly where it is. It's just listening to what the driver is saying, right? The drivers are basically being the sensors of the drivetrain. But in the auto's case, the driver can't input any like commands based on what the driver is seeing. So we need to use these built-in encoders or sensors on the motors to figure out where we are. Now, these encoders, they measure stuff in ticks, which are small measurements. Basically, it ticks over a certain amount of times per rotation. So these motors will tick over about, I think they go at 430 RPM, which is about, I believe, I'm not exactly sure what the ratio is for it, but I think it's like 800 ticks or 1,000 ticks per revolution. But basically, we'll find that out now when we do it. But basically, the calculation that is needed, you can see here I've got a bit of a slide. The wheel circumference is the distance the robot will travel if the wheel rotates, right? And it is directly proportionate to the distance that the encoder reads per full rotation. So if you rotate the motor once around, the encoder will read a given amount of ticks for that amount of rotation. So let's say, like I was saying, it's about 800 ticks. And the wheel's circumference determines how many centimeters that moves the robot forward. So in the case of these wheels, I believe they are, let's just check here. Let's go to the starter kit where you get the stuff. Let's go to the wheels. Let's see, we've got the motors. Yeah, there, we got wheels. So we got 96 diameter wheels, right? Wait, is that the correct one? Oh, that's the Rhino wheels. We've actually got, oh no, this is the correct one, okay. So then 96 diameter, whoops, wrong shortcut. So we got 96 millimeter, right? So 9.6 centimeters. So we say 9.6 centimeters times 3.14 to get the circumference. So that basically means if the motor rotates once around, our robot is going to move 30 centimeters forward. What we want to do in the code here is we want to store some constants. So we want to say double wheel, wheel circumference. I'm not going to write the whole thing out because it'll take too long. And we're going to say 30, right? And this is in centimeters. In centimeters. Then the same thing here. We say double. And what is the other thing? So now we want to know how many ticks. You can see here, using drive encoders for auto navigation, the motor target equals the target distance times the ticks per centimeter. So we want to be able to, basically what this means is we want to be able to input a amount of centimeters the robot must travel, and it needs to convert those number of centimeters into something that the robot can understand, which, like I've been talking about, is ticks. So the ticks per centimeter value is the motor ticks per revolution, how many ticks the motor reads if it rotates once, divided by the wheel circumference. So we've already got the wheel circumference here, right? But we need the ticks per revolution. So ticks per rev. And now we need to find these for the motors that we have. So if we go up to this is the starter kit, right? We go up to the top, we've got these motors here. And they're these motors. So we can just grab these motors. You can see they are 312 RPM. So now how exactly do we figure out how many ticks they have? We should be able to just search them, which is the easiest way. We go to the top, we put them into Gobilda search menu. We go over here, you can see they're 312 RPM, shaft, whatever. We go down here and we say its encoder resolution is 537 per rotation at the output shaft, which is basically our motor ticks per revolution. So what we want to do in here is we want to say our motor ticks per revolution equals 537, which is the motor that you get in starter kit and you will be using in the Gobilda starter bot. So now that we have that, we can create that value I was talking about, right? The ticks per centimeter, which is the motor ticks per revolution divided by the wheel circumference in centimeters. So we say it's motor ticks, right? Ticks per rev, not get ticks per rev. Oh, so we want to say this value is called the ticks per centimeter, right? So how many ticks does the motor need to travel to move the robot 1 centimeter? And this is the motor ticks, right? Ticks per rev divided by the wheel circumference. Right. Now we can use that value to actually to find the motor target based on the distance we want to drive. But now to actually drive it, there's a lot more code that goes into that. Maybe I can go through it quickly now. Let's see how much time have I got left. Yeah, I can probably go through it quick. I'm going through stuff quite fast, but I think that's okay. If you have any questions, you can always put them on the Discord. So yeah, so now what we need to do is, right, we can find the distance the robot needs to travel forward to drive that amount of centimeters. But we need to actually create a way of telling the motors to move that amount. So there's one other thing I noticed here. You can't actually copy directly over from the teleop because you want to use the encoders, you actually need to say stop and reset encoders first in the init period, and then you're going to say run using encoder. Okay. And then down in here, or no, actually after the method, so outside of this method, you're going to want to create another thing. And this is the first time we're going to look at a method in this course. So basically what it is it allows you to call a chunk of code elsewhere in your code. So you can see here as an example, I create a public void drive distance. So this is going to allow us to call the drive distance and tell the robot how much we want to travel forward or backwards. So what we want to do is we want to take in, so in these curly braces, that's basically where it allows you to take in a value when you call it, because we want to take in how many centimeters we want to travel, right? So we want to say target centimeters. Okay. And then you can see up here in our auto after the wait to start, we can actually say drive distance, and you can see it wants a value here in target centimeters. I can put in 10. And that allows us to tell the robot how far to drive without having to keep putting in all of the code again. What do we have to do first? So first, like I was showing in this right here, we need to find the motor target. So we have the value we need to find the motor target, but we actually just need to find it. So we're going to create another variable called motor target equals target centimeters multiplied by ticks per centimeter, which is the value that we created earlier, right? And that's going to give us the amount of ticks the motor needs to travel to reach the target centimeters that we inputted. So now that we actually have the target, right, in a form that the robot can actually understand or drive forward to, we can actually just set it to drive that amount. So we can copy this up here in our init thing, and we want to stop and reset the encoders, and then what we want to do first is we want to say left drive dot set target position, right? This is the target position of the motors in ticks, so that's what we've already got. To motor target, right? Except we actually need to make this an int because motors can only use whole numbers. Encoders can only use whole numbers that don't have decimal points on them. And then we want to do that for both of these. Right? And then the last thing we want to do is we want to copy this again. Actually, no, it's not the last thing, but it's close to the last thing. And then we want to say run to position. And this is gonna, not the right thing. This is gonna actually drive the motors to that target position that we have got, right? So we're setting it to our target position in the motor target in ticks, and then we're saying run to that position. Now, the last thing we want to do is we actually want to wait until it gets to that position, because otherwise then it's just going to go through everything really fast and not actually wait until one step finishes to move to the next step. So what we'll say is we'll say while left drive dot is busy. So that's while it's busy driving it to the position, we're going to do nothing. So we're just going to wait here until it gets to the right position, then we can move on to the next thing, right? So that's the basis of the auto, of the kind of framework and the first kind of driving distance. You can see here we have the example we were talking about here, is you want to drive a certain amount. So because you're starting almost right here, all you're going to want to do is drive forward like 10 or 20 centimeters. So you can see down here, you can say drive forward 20 centimeters. And basically that'll just drive it forward for now. Obviously I won't do the arm yet. But I think that is all I'm gonna finish with today. And then next week we'll talk about how exactly you can put your arm code and your gripper code to actually drop the sample off in the basket correctly. So yeah, thanks so much for watching the video, and I will see you guys in the next one next week to finish off this auto code. I will also be doing another recording sometime in the middle of next week or the beginning of next week about how this code needs to be modified to work for the Rev Start bot up to this point, and then we'll do the same thing again after next week's session to finish that one off as well. Just so we cover everything we need to about the auto. Yeah,